3-Eye Atlas is a comet from another solar system. But Harvard scientist Avi Loeb claimed on this show a couple of weeks ago.
It's basically, we see how much material is evaporating from the surface of the object in the direction of the sun.
The images appeared first as little more than spectral flashes, threads of light stretching across the blackness near the sun's edge, caught by one of NASA's heliospheric observatories. But when Avi Loeb, the theoretical astrophysicist known for his fearless curiosity about interstellar visitors, analyzed the sequence, he noticed something extraordinary. The images seemed to show 3-Eye Atlas, the third known interstellar object to enter our solar system, flaring with an intense focused jet aimed directly at the sun. For decades, astronomers had imagined that objects passing between stars were mostly inert, frozen relics of distant planetary systems. Yet the behavior captured here defied all prior understanding. A cold, tumbling interstellar rock firing a directed jet toward a star was not only improbable, it was supposed to be physically impossible. Before we start, hit the like and subscribe buttons for more exclusive news. At first glance, the shape and motion of the luminous feature resembled the classic discharge of a comet outgassing under solar heat. But 3-Eye Atlas was not behaving like any comet. Instead of the jet trailing away from the sun, pushed outward by radiation pressure, it appeared to be directed toward it. That reversal upended one of the most fundamental principles governing the dynamics of sublimation and solar-wind interaction. To Loeb and the small team of analysts working with the high-resolution data, it suggested something far stranger was at play. Either an exotic composition reacting to sunlight in an unknown way, or a controlled propulsion event, deliberate or at least self-organized beyond any natural explanation. Each frame of the NASA imagery seemed to whisper that humanity was looking at a process foreign to known celestial mechanics. The object, 3-Eye Atlas itself, had already drawn attention when it was first identified months earlier, streaking into the solar system on a steep hyperbolic trajectory. Its path, like that of Oumuamua and Borisov before it, confirmed its origin beyond the sun's gravitational grasp. But this one carried a peculiar spectral signature. Observations indicated anomalous reflectivity and rapid changes in brightness, suggesting an irregular surface that rotated far too fast to be stable if it were an ordinary conglomerate of rock and ice. Loeb's analysis of the new images deepened the mystery. Near perihelion, just as the object approached its closest point to the sun, an energy plume erupted from one hemisphere, forming a narrow beam of plasma and dust that appeared to align precisely with the sun's core. It was as though 3-Eye Atlas were releasing energy toward the star itself, in defiance of the natural flow of radiation. Astrophysicists scrambled to reconcile what they were seeing with known physics. Traditional cometary jets result from volatile compounds vaporizing under sunlight, producing outward thrust. To eject material sunward would require an inversion of pressure gradients or magnetic forces strong enough to overcome the solar wind. An almost impossible scenario for a small, inert object. Some theorize that perhaps the jet was an optical illusion, an effect of viewing angle combined with reflection from the coma. Others suggested that electromagnetic interaction with the sun's magnetic field might have induced a directed discharge. Yet the consistency of the jet, maintained over several hours of observation, hinted at coherence rather than chaos. Loeb, known for his willingness to challenge orthodoxy, proposed that 3-Eye Atlas might contain internal mechanisms or materials capable of manipulating solar energy directly. That idea, however speculative, was not without precedent in Loeb's thinking. Years earlier, he had proposed that Oumuamua could have been a light sail, an artificial object propelled by radiation pressure. The scientific community had reacted with a mixture of fascination and skepticism, but now, confronted with images of an interstellar body apparently releasing a controlled burst of energy, the balance between doubt and possibility began to shift. If 3-Eye Atlas were indeed expelling a jet toward the sun, it implied intent or at least design. It might represent technology from another civilization, a probe maneuvering using solar interaction. Even if not artificial, such a mechanism would redefine the boundaries of what natural bodies could do. It forced astronomers to consider the physics of interstellar materials forged in environments utterly alien to our own. The implications reached far beyond astrophysics. The idea of an interstellar object engaging dynamically with a star, of a fragment of another system effectively responding to solar radiation, challenged assumptions about the inertness of the cosmic debris passing through our neighborhood. If 3I Atlas had internal energy sources or self-regulating reactions, it would mean that the chemistry of some interstellar bodies operated under entirely different rules. Perhaps exotic ices or superconducting minerals interacted with sunlight in ways that produced electromagnetic thrust. Or perhaps the jet was a form of plasma discharge, a phenomenon linked to electric potential differences accumulated across interstellar travel. Whatever the cause, the behavior opened a new domain of astrophysical inquiry. The NASA imagery that revealed this event came from multiple instruments: the Solar Dynamics Observatory, the Parker Solar Probe, and even the SOHO spacecraft, all capturing the sun from different vantage points. When Loeb cross-referenced the data, the alignment of the flare from 3I Atlas remained consistent. It was not a glitch or compression artifact. It was a genuine ejection of material at high velocity. Spectral analysis indicated ionized carbon and oxygen, suggesting that the material was being energized by intense electromagnetic forces. The jet appeared to originate from a localized region on the object's surface, perhaps a fissure or cavity that had accumulated charge as 3I Atlas traveled through interstellar plasma. When the object encountered the sun's magnetic environment, that charge might have discharged violently, producing the jet. Yet even this electromagnetic explanation left open questions about the directionality and sustained nature of the emission. As Loeb presented his preliminary findings, reactions across the astronomical community were divided. Some hailed it as one of the most compelling pieces of evidence that interstellar objects could possess active dynamics. Others cautioned against premature conclusions, noting the risk of confirmation bias in interpreting ambiguous data. Still, the fact remained that the images displayed a phenomenon that did not fit established models. The energy output estimated from the observed brightness was substantial, equivalent to several tons of matter expelled per second. That magnitude of activity from an object only a few hundred meters across was unprecedented. If natural, it represented a new category of interstellar chemistry. If artificial, it hinted at the presence of technologies far beyond human capability. The sequence of frames showing the jet's evolution became the focus of intensive study. The beam first appeared as a faint linear streak, then brightened rapidly, maintaining a stable orientation relative to the sun. Over the course of several minutes, it elongated, forming what looked like a narrow bridge of light between the object and the star's limb. The shape pulsed slightly, almost rhythmically, before dissipating into a diffuse cloud. That regularity intrigued Loeb. It suggested modulation, perhaps a feedback process or a sequence of discharges. Natural outgassing events are typically erratic. This one seemed almost tuned. The possibility that 3I Atlas was using solar energy to alter its trajectory or slow its approach could not be dismissed. Such control would make it the first known object from another star system to exhibit active navigation. If that were the case, humanity had just witnessed a demonstration of interstellar propulsion in action. The idea that a small probe could use the sun's gravitational and electromagnetic fields as part of a maneuver had long been theoretical. In concept, a craft entering a stellar system could convert kinetic energy through controlled plasma emission, effectively braking or redirecting itself without chemical fuel. The jet observed from 3I Atlas matched the energy profile such a mechanism might produce. For Loeb, who had often spoken about the probability of technological relics traveling through space, this was tantalizing confirmation that advanced engineering might persist long after its creators were gone. Even if no civilization remained, the devices they built could still wander the galaxy, interacting with stars as part of self-maintaining programs written in physics rather than code. The strangeness of the event also reignited philosophical debates about our place in the cosmos. For centuries, humanity had looked outward and seen only silence, a universe vast and indifferent. But if 3I Atlas was more than rock and ice, if it contained the remnants of design or purpose, then the gulf between civilizations was not one of existence, but of recognition. The jet toward the sun might be a signal, a stabilization maneuver, or a simple reaction, but its existence forced the realization that intelligence might leave fingerprints on the fabric of space long after it ceases to speak. Loeb's interpretation leaned toward curiosity rather than certainty. He saw in the images not proof, but possibility, the invitation to treat anomalies as data rather than dismissals. From a purely scientific perspective, the phenomenon demanded new models. The idea of a sunward jet required rethinking how energy and matter behave under extreme gradients of temperature, radiation, and magnetic flux. The heliosphere is not empty. It is a turbulent sea of charged particles. If an object carried conductive materials or trapped magnetic fields, entering that environment could trigger complex plasma interactions. Laboratory simulations hinted that, under the right conditions, dust aggregates embedded with ferromagnetic inclusions could discharge energy along preferred axes. Perhaps 3I Atlas was such an aggregate, a relic of a magnetic world, carrying internal structure that responded dynamically to solar influence. Yet even this scenario struggled to explain the sustained collimation of the jet. Natural plasma discharges disperse rapidly. This one remained narrow and coherent. The coherence of the beam led some to propose resonance effects. The sun's corona vibrates with oscillations that can induce standing waves in nearby plasma. If 3I Atlas had a conductive shell, it might have acted as an antenna, channeling energy along magnetic field lines. The jet could then be the visible trace of that energy release, a phenomenon akin to lightning but scaled to interplanetary proportions. Loeb's team modeled this interaction and found that it could, under certain assumptions, produce the observed geometry. But the energy required to initiate such a discharge remained unexplained. Where would an interstellar rock store that much potential? The answer, if one existed, lay buried in the unknown history of the object's origin. Perhaps a fragment of a shattered planet orbiting a magnetar or an ancient white dwarf carrying residual magnetism from a stellar catastrophe. As the images circulated among researchers, speculation widened. Some noticed that the jet's orientation relative to the sun's magnetic field lines matched patterns seen in coronal mass ejections. Could it be that 3I Atlas had triggered a local perturbation, a feedback loop between its own electromagnetic field and that of the sun? If so, the object had not merely emitted energy, but had interacted dynamically with a star's atmosphere, something no asteroid or comet had ever done. This possibility fascinated heliophysicists. The sun's behavior could be influenced by even small intrusions of conductive matter. Understanding that interaction might illuminate broader processes in stellar magnetism. Loeb's discovery thus straddled two disciplines, the study of interstellar visitors and the physics of the sun itself. The event also tested the limits of observational technology. NASA's instruments were never designed to capture such fleeting small-scale features near the solar limb. The fact that the jet was visible at all spoke to its brightness and coherence. Future missions might now prioritize higher-resolution imaging of interstellar objects passing close to the sun. The chance of witnessing another event like this was small but not impossible. Each new detection expanded the catalog of anomalies, shaping a growing picture of how the galaxy exchanges material between systems. In that sense, 3I Atlas became a messenger not just of mystery but of connection, a physical link between the stars and the processes that sustain them. For those following Loeb's career, the discovery seemed like a culmination of themes he had pursued for years. The search for interstellar relics, the openness to unconventional explanations, and the conviction that the universe might already be filled with evidence of intelligent origin, if only we looked carefully enough. His interpretation of 3I Atlas did not claim certainty. Rather, it argued for the legitimacy of asking forbidden questions. Why would an object emit energy toward a star? What mechanisms could reverse the direction of radiation pressure? How could an interstellar fragment maintain internal energy over millions of years of travel? Each question peeled back a layer of assumption that had defined modern astrophysics since the Enlightenment. On a practical level, the event encouraged collaboration between disciplines that rarely overlapped. Plasma physicists, planetary scientists, and astrobiologists all found reasons to study 3I Atlas. The idea that interstellar bodies might interact electromagnetically with stars opened the door to new kinds of detection. Instead of relying solely on optical telescopes, future searches could monitor radio emissions, magnetic fluctuations, or X-ray bursts associated with such encounters. If 3I Atlas had indeed discharged energy, it might have left detectable traces across the electromagnetic spectrum. Recovering those signals could provide direct insight into its composition and structure. In that sense, the jet was not just an anomaly. It was data in the purest form, a new way of reading the behavior of matter that originated light years away. The physics of the jet also carried implications for the nature of interstellar travel. If a small object could generate directional thrust through electromagnetic discharge, then interstellar propulsion might not require massive engines or exotic fuels. It could rely instead on harvesting local fields and gradients, using physics itself as the engine. This idea, once the province of speculative engineering, suddenly had observational grounding. A self-propelled fragment could cross the galaxy over eons, adjusting its trajectory by interacting with the magnetic and plasma environments of stars. Whether natural or constructed, 3I Atlas illustrated that the boundary between physics and technology might be thinner than imagined. Nature, given enough time and complexity, could engineer itself. Loeb's insistence on treating the event as real rather than illusory forced others to confront uncomfortable possibilities. The tradition of skepticism in science is vital, but so too is the courage to follow evidence beyond expectation. The jet toward the sun may yet find a natural explanation within known physics. But until that explanation emerges, it remains one of the most intriguing signals ever captured. The fact that it occurred at all demonstrated that our understanding of interstellar matter is incomplete. Every time a new object like 3I Atlas enters the solar system, it carries the memory of its origin, chemical, magnetic, and structural signatures that encode the history of alien worlds. The sun, by interacting with those travelers, becomes a lens through which we glimpse the diversity of cosmic creation. As analysis continued, attention turned to the timing of the jet relative to 3I Atlas's rotation. If the emission correlated with its spin, that might indicate internal structuring, a region that consistently faced the sun during the discharge. Preliminary data suggested such periodicity, reinforcing the impression of coordination. Even if purely physical, it implied a degree of regularity absent in typical cometary behavior. Some speculated that the object's internal composition might include pockets of superconducting material capable of channeling current efficiently, leading to repeated bursts as magnetic stress built and released. That would make 3I Atlas not merely a rock, but a dynamic electrical entity carrying within it the capacity for complex, self-modulating behavior. Theoretical modeling of such superconducting inclusions drew attention to the environments in which they might form. High pressure, high magnetic fields near neutron stars or magnetized protostellar disks could produce crystalline phases unknown on Earth. If fragments from such regions were ejected into interstellar space, they might preserve those properties indefinitely. Encountering the sun's magnetosphere could then awaken dormant energies, producing spectacular discharges like the one Loeb observed. This scenario did not require alien technology, only alien geology. Yet even that naturalistic explanation expanded the horizons of planetary science. It meant that interstellar matter could carry physical properties so extreme that our solar system's conditions seemed tame by comparison. As word of the event spread beyond academia, public imagination seized upon it. The notion of a mysterious object firing a jet at the sun evoked images of cosmic drama, a silent duel between a wandering emissary of another world and our own star. Artists, philosophers, and science communicators found in the story a metaphor for curiosity itself, the act of confronting the unknown with directed energy, of engaging the universe not passively but boldly. Loeb's calm, methodical explanations only heightened the wonder. He spoke not of aliens or miracles, but of data, of light captured in instruments built by human hands, revealing behavior that demanded humility before nature's ingenuity. The poetry of the event lay in its ambiguity. We did not yet know what we were seeing, but we knew it was real. In private discussions among researchers, the jet's implications for planetary defense were also considered. If interstellar objects could emit energy or interact dynamically with solar radiation, predicting their trajectories became more complex. Traditional models assume purely gravitational motion. An object capable of self-propulsion, however minimal, could deviate unpredictably. Understanding such mechanisms was not merely academic. It affected our ability to track and, if necessary, mitigate future interstellar intruders. 3I Atlas, by demonstrating active behavior, had effectively announced a new class of celestial body, interstellar actives, objects whose physical interactions with stars rendered them participants rather than bystanders in solar dynamics. Throughout the analysis, Loeb emphasized the importance of openness. He urged colleagues not to dismiss anomalies as errors simply because they seemed to violate expectations. Science, he argued, progresses by confronting the impossible until it becomes possible. The images of 3I Atlas, whatever their final interpretation, embodied that process. They reminded observers that every major discovery in astronomy, from the motion of the planets to the expansion of the universe, began as an inconsistency in data. To see a jet firing toward the sun was to witness such an inconsistency in its purest form. The challenge was not to explain it away, but to understand what deeper truth it revealed. From a cosmic perspective, the encounter symbolized the meeting of two travelers. One, our star, ancient and stable. The other, a messenger from the deep interstellar night, carrying unknown histories. Their brief interaction produced a flash of light that bridged systems separated by light years. In that flash, humanity caught a glimpse of how dynamic and unpredictable the universe truly is. The laws of physics remained intact, yet their application in untested conditions could yield wonders that bordered on the miraculous. The jet of 3I Atlas was one such wonder, a reminder that even within the rigor of data and equations, the universe retains the capacity to surprise. The continuing study of this event promises to reshape how scientists approach the next interstellar visitors. Instruments may now be tuned to detect not only reflected light but active emissions. Missions could be designed to intercept such objects, capturing high-resolution data before they vanish back into the void. Each new observation will refine our understanding of the boundary between natural and artificial, between randomness and order. Whether 3I Atlas turns out to be a natural superconducting relic or a remnant of distant engineering, its jet toward the sun stands as evidence that the cosmos is richer and stranger than our models allow. What makes this revelation so compelling is how it redefines the sun itself. For most of history, the sun has been viewed as a singular actor, the gravitational monarch around which planets and comets dance. Yet in the interaction with 3I Atlas, the sun becomes a participant in a dialogue, responding subtly to the intrusion of an object from beyond. Magnetic fields flex, radiation pressure fluctuates, and streams of plasma shift in rhythm with the incoming visitor. The event transforms the star from a passive backdrop into an active partner in a cosmic experiment. It shows that stellar systems are not sealed ecosystems, but porous laboratories, open to influence from the galaxy at large. Every star, including our own, may occasionally host these mysterious exchanges, moments when something from far away taps its energy, siphons or redirects it, and then departs, leaving only traces for careful observers to decode. This concept challenges the way scientists think about stellar environments. If interstellar fragments can induce local perturbations in a star's magnetosphere, they may play a role in stellar evolution that has gone unnoticed. A single encounter might be negligible, but across billions of years and countless intrusions, such interactions could shape a star's corona, redistribute angular momentum, or even contribute to the distribution of elements in its atmosphere. The sun's variability, long a puzzle to solar physicists, could be influenced not just by internal cycles, but by the subtle fingerprints of interstellar debris. Loeb's discovery may thus open an unexpected avenue of research linking heliophysics and galactic dynamics, how the vast flow of matter between stars can seed activity in otherwise stable suns. From another perspective, the event sheds light on the architecture of the galaxy itself. Every interstellar object is a messenger carrying information about its home system, the chemistry of its formation, the radiation environment it endured, and the physical processes that ejected it into the void. To witness one interact with a star gives astronomers a direct kinetic insight into those origins. The jet toward the sun might encode data about magnetic field strength, rotational inertia, or residual charge accumulated over millions of years. Studying the exact form of its emission could allow scientists to reconstruct conditions in distant systems, like deciphering a postcard written in the language of plasma and light. For the first time, humanity could begin to map the invisible bridges that link stellar families across interstellar space. Beyond the astrophysical implications, the discovery ignites something deeper, a recognition of the universe's dynamism. Human thought often divides existence into the living and the inert, but the cosmos seems to defy that dichotomy. Here was an object, cold and ancient, performing what looked like an act of expression. It was not conscious in any human sense, yet it displayed responsiveness, an ability to interact purposefully with its environment. This blurring of the line between mechanism and agency compels a philosophical reconsideration of what it means to be active in the universe. Perhaps activity is not limited to life. Perhaps the universe itself is a continuum of self-organizing behaviors, from the dance of molecules to the vast interplay of stars and their visitors. 3. I-Atlas becomes a symbol of this principle, an emissary of cosmic vitality manifesting where least expected. The possibility of internal structure within 3 I-Atlas adds another layer of intrigue. If the jet was produced by built-in conductivity channels, it suggests that the object's interior may not be uniform. Layers of differing composition could act as capacitors or insulators, storing and releasing energy in bursts. As it tumbled through the sun's magnetic field, these layers might have aligned momentarily, producing a focused discharge. Such a process would hint at a complexity of formation unseen in ordinary comets. It might point to planetary engineering within its system of origin or to geological processes under extreme conditions that yield ordered electromagnetic properties. Either explanation extends our understanding of how diverse the material universe can be. This line of thought inevitably raises the question of whether 3 I-Atlas represents a natural phenomenon on the threshold of technology. Nature, given sufficient time and scale, often produces arrangements that mirror human invention. Just as crystals imitate the logic of architecture and biological molecules mimic machines, an interstellar body might evolve properties that resemble propulsion systems. The jet toward the sun, then, could be a naturally occurring analog of a drive, a product of physics converging on efficiency. In that view, technology itself is not an anomaly, but an emergent expression of the universe's tendency towards self-organization. Loeb's interpretation does not need to rely on aliens or artificiality. It can point to the profound continuity between the natural and the engineered, both guided by the same fundamental laws seeking pathways to order. The excitement around this discovery also underscores the growing synergy between observation and computation. The raw images from NASA's observatories would have remained enigmatic without sophisticated modeling to interpret them. Loeb's team employed simulations that combined magnetohydrodynamics with radiative transfer models, iterating through thousands of possible geometries to reproduce the jet's behavior. Each simulation revealed new subtleties: the influence of rotation on the beam's stability, the way solar flux density altered emission intensity, the possible precession of the object's axis under magnetic torque. These insights not only explained what was observed, but also generated predictions for future encounters. Science progresses through such loops of feedback, data inspiring models, models refining observation. In this sense, 3 I-Atlas has become a test case for the next generation of cosmic detective work. As word spread through the international research community, observatories across Earth turned their instruments toward the region where 3 I-Atlas was last seen. Ground-based telescopes captured its fading glow, and radio arrays searched for lingering emissions. Although the object was already outbound, the after effects of its passage, perturbations in solar wind density, ripples in the heliospheric current sheet, could still be detected. By comparing these subtle changes with pre-event baselines, scientists hope to quantify the magnitude of the interaction. The sun's outer atmosphere is an exquisitely sensitive instrument. A single injection of charged material can propagate measurable effects for weeks. Detecting such traces would confirm that the event was not merely visual but energetic, a real exchange of matter and momentum between star and visitor. If confirmed, the energy budget of the event could offer clues to the mechanism behind the jet. Calculations suggest that the beam's luminosity corresponded to power levels far exceeding what sublimation alone could produce. That excess implies either an internal source of stored energy or an external amplification via resonance with the solar magnetic field. In both cases, the physics extend beyond conventional cometary models. A body that can momentarily tap into stellar magnetism to amplify its own emission acts almost like a transformer, converting one form of cosmic energy into another. This would mark the first direct evidence of energy transfer between an interstellar object and a star, a phenomenon previously considered purely theoretical. The discovery also revitalizes interest in directed energy research. If natural objects can channel and focus energy with such precision, humans might one day learn to replicate the process for propulsion. Studying 3I Atlas could inspire designs for future spacecraft that use controlled plasma jets or magnetic field coupling to maneuver near stars without carrying fuel. Nature often provides the blueprint for technological leaps. Just as the flight of birds informed aviation, the behavior of an interstellar traveler could inform the mechanics of interstellar flight. Loeb himself has long advocated for light sail technology, and the parallels between that concept and the sunward jet are impossible to ignore. Both rely on leveraging stellar energy, both achieve motion through radiation interaction, and both illustrate the universe's elegant economy of power. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on 3I Atlas shooting a jet at the sun? We want to hear from you. Thank you for watching, and see you next time.